and introducing the different speakers. So this webinar is organized by the Interreg Northwest Europe project WOW, a project that looks into the recovery of valuable resources from sewage. But much more about this project later on during the several presentations that are giving. And it's very good to see that so many people are interested in the recovery of valuable resources from wastewater. We had more than 100 people applying for this webinar, and I still see people dropping in, so welcome everyone. As you know, this topic perfectly matches the sustainable goals of the EU that are described in the Green Deal. So it's the recovery of valuable resources from wastewater focuses on recycling and reuse, so using less virgin resources. It also aims for reduction of CO2 emissions, and on the side it also tackles water scarcity and quality. So I think for today we have a very interesting program with various examples of different European projects that are running at this moment. And considering time, I won't be talking too much because I'm much more interested in the presentations of the different speakers. Very briefly, some rules for the webinar. I think everyone is accustomed to it already, but just to be sure, I would like everyone to put their microphone and camera off during the presentation, so I have a more stable environment for the presentations. If you would like to ask questions, you can ask them in the chat, so I will be monitoring the chat. But at the end of the presentation, you can also raise your hand and ask the question live, and then turn on your camera and microphone, of course. And that's also nice for the speaker to see who was asking the question, but the choice is up to you. We will record this session, mainly the presentation, so they can be viewed afterwards, and we will not tape the question and answers. But if you have problems with being in front of the camera or speaking up, then just turn off your camera and turn off your microphone. So then you should be fine. So then let's go to the first speaker or speakers of today. So we have two speakers for the first presentation. We have Professor Heidrun Steinmetz of the Department of Resource Efficient Wastewater Technologies of the University of Kaiserslautern, where she focuses on concept and technologies for resource efficient wastewater management. And she will have a second speaker, which is Rosalia Persiani, who works at Avans University of Applied Sciences as a researcher, where she looks into resource recovery from sewage. So I will give the word to you, Heidrun. And Wendy, can you share the presentation?
Okay, thank you, Jappe, for the nice introduction. And I think I could share the presentation as well now, Wendy. Should I try, or is it faster if you do?
Yeah, please try.
I'll try. It should work now. Let me see. Which one is it? Oops. Oops. You see it now?
Yes, it's there, Heidrun. Yeah.
Oh, okay. Does not move totally like it should, but anyhow. So yes, thank you for the nice introduction, Jappe, and dear ladies and gentlemen, it's a pleasure to give you a first insight about our first experience with PHA production and pilot scale project, which is run on the sewage treatment plant in Wuppertal-Buchenhofen. And you see here on the left side the container, so that's the size in which we are working. That was a winter impression, but fortunately we have now the summer situation. So let me first shortly introduce about the different pilots which we have in our WOW project. In WOW we focus on the organic carbon, and we have different parts where we want to collect the organic carbon and make valuable material out of it. The first one is here at the beginning. There we use the fine screens in order to gain cellulosic material, and from that we can produce at the end char, oil and fatty acids, but that's not the focus of today's or my presentation. So I give first an introduction to the third one, which is also not focus of the presentation. That's the use of the dissolved organic carbon, which can be enriched as long-chain fatty acids via Microtrix parvicella cultivation, and that these lipids we can use at the end for biodiesel production. And what I would like to talk about today is about the usage of the primary sludge and the carbon content in the primary sludge. So what we do there is that we use that in a two-step process, which I will show you soon a bit more closer, in order to force the bacteria to enrich PHA, and afterwards it's extracted, and then it should be compounded. We are in that process now. So, okay. So the PHA pilot team, it's mainly 4 partners. The first is the enrichment of the bacteria and the production that's done by us at the wastewater treatment plant in Wuppertal. Then the extraction, that what Avans Applied University does and what Rosalia will present within this presentation too. And if that works properly, then the next steps will follow. That's the extrusion and the injection in order to make a good product out of it. And all these data which we gain in this pilot operation will be brought into the technical economical analysis afterwards, which is done by Vito. So the presentation focuses on these 2 steps today. Let me shortly introduce the process. We have a 2-step process, as mentioned. The first one is an anaerobic reactor, then a solid liquid separation, and then in the second phase we have an aerobic reactor. Partly we have a side stream in order to select, to accumulate the biomass, which is able to store more PHA than normal biomass will do. And what are the products? We hope that the bacteria enrich them. It's mainly PHB and it's PHV. So both of them we find at the end in the process. What is happening there? So we have, of course, the large molecules like carbohydrates, proteins, and fats. They are within the normal process in this case, under anaerobic conditions, hydrolyzed to the monomers, amino acids, long-chain fatty acids, glycerol, and so on. And what we aim is these red-marked volatile fatty acids. So the first step of the anaerobic digestion should take place in order to gain acetate, butyrate, valerate, and propionate. But then we want to use this material as substrate for the aerobic PHB and PHV production, and we want to stop at this point the acetogenesis and the methanogenesis. And that means we need certain boundary conditions which we have implemented at our pilot plant. And that's in order to suppress the methane fermentation, we have a pH which should be lower than 6. We have a retention time which should be lower than 8 days. And then we can produce the volatile fatty acids for the PHA production. So let me show the pilot. Anything goes wrong or just somebody has opened the mic? Okay, let me show the pilot. So we give in the primary sludge and have a working volume in this acidification reactor of 1.3 cubic meter. From there, after acidification, about 1 week, we separate the supernatant via a chamber filter press that goes in the VFA storage tank. And from there, we have 2 reactors, as you can see here. One is the enrichment or the selection reactor, where we use this substrate, the VFA substrate, and excess sludge from the wastewater treatment plant in order to enrich bacteria which are able to produce PHA, and the other one is the accumulating reactor. After accumulation, we use the same chamber filter press, and then we have a drying cabinet, and afterwards the enriched biomass from our pilot. So the objectives of this pilot operation is that we want to have a long-term operation under real condition. That means also all seasons. I showed you the winter situation. Now we have more or less a summer situation. So we want to know, do we have a stable VFA composition and do we have a stable PHA composition? Of course, we want to learn, and we have already learned a lot about the operational aspects. Do we need aid material like flocculants or chemicals for acidification and so on? How properly is the dewatering device running and so on? And at the end, we want to elaborate knowledge at the base for full-scale implementation in order to give hints for the planning process and the operation of full-scale plants. Here I brought along a few results concerning the volatile fatty acid composition, and what was very nice. So if you look at the time scale, these results are examples from August till December. So it's summer, autumn and winter time operation. And we recognized that we have a relatively stable concentration of the VFA COD part. And that was very nice, a relatively stable composition. So it's about 40%, 35 to 40% of acetic acids, around 45% of propionic acid, and around 10 to 15% of butyric acid, and the rest are smaller fractions. So if we look at that, we have more or less equal parts of even C atom molecules and uneven molecules. And that's interesting for the following PHA production process. So the first results we gained from the pilot operation was that first we have to struggle really a lot with some relatively simple, maybe technical parts, but that took a lot of time. For example, in a pilot plant, it's not so easy to have a really dense reactor, so we had to struggle with some H2S production problems and to implement exhaust air and to make the reactor more dense. We had problems with the dewatering in the chamber filter press, so now we use perlite. We didn't want to use organic flocculants in order to produce organic polymers, so that was a bit why we took this unorganic material, but that needs to be improved, and that's why we want to use in future centrifuge to avoid these 8 flows. And so far we have 6 nice samples from the PHA, which we have analyzed at our lab, we have around 13% PHA per gram total suspended solids. That is something, but it needs to be improved, definitely. And we have a ratio of about 1/3, which is butyrate-based polymer, and 2/3, which is valerianate-based polymer. So at this point, I would give to Rosalia. She tells a bit more to the analytical part of these polymers.
Yes, so at once we received the batches from Kaiserslautern University, and we tried to make some more analytics on them and give the feedback. So by now we got the first batch. The first batch from the TUK, and it was produced with enriched biomass and synthetic feed, and addition of perlite as filter aid, as Heidrun said. And now this is the first batch, but we have received different batches with decreasing the amount of perlite. And this is how it looks in the picture, the biomass with perlite. And next slide, please. So at Avance, we have developed an optimization of the green extraction with the dimethyl carbonate, and we optimized the biomass to the solvent ratio and the extraction time. After we extract the PHA from the biomass through reflex extraction, we can characterize the PHA with thermogravimetric analysis, and then the PHA monomer composition through GCMS. Next slide. So for the first batch we received, we have a general characterization of a very low moisture content to around 2%, a biomass ash content, which also includes the amount of perlite that's added here. It's around 62%, and the PHA content in the biomass that is around 33%, and the extracted PHA yields 13.75%, and it's similar to the results that Heidrun already showed. But after we subtract the ashes of the added perlite, we can see that there's a 36% of PHA in our biomass, and the purity after the extraction is around 91%. Next slide. This purity we can see by comparing the pH content before and after the extraction of the PHA, and in the picture you can see how the extracted PHA looks. We tried a bigger scale extraction with increasing the amount of biomass that is being extracted by 10 times to 50 grams, but because we need to decrease the amount of solvent that we use if we want to have a bigger scale extraction. But this showed that increasing the biomass solvent ratio to 20, we have a PHA extraction yield that is 10% lower than if we were using 6% biomass to solvent ratio. With the GCMS, we use sulfuric acid and methanol. The PHB polymer is hydrolyzed by sulfuric acid and then is reacted with methanol. And as Heidrun showed, our results are very similar. And we have an HB content of 37 and HB content of 62. Yeah, and this is an example of a chromatogram. We can see the two peaks are the main monomers that we're looking for, and we can also see if there's what impurities are present in the PHA that is being extracted. Thank you.
You're muted, Heidrun, so if you...
Oh, okay, so sorry. Now it should work. Okay, so I take over for the conclusion. We want to gain more insights into the operational needs with the long-term operation. We have already some of it, but we will run the pilot plant for a longer time in order to figure out if we have really for a year stable conditions concerning the whole process, that we have the stability of the process, and that the operation with the real devices will function. So far we have some good results, but there's still a need of improvement. The first results have shown that we have a stable VFE composition and a suitable PHA composition, but need to improve the PHA amount. And what was quite nice, that the pilot the PHA produced in the pilot plant shows similar results like that one produced in the lab scale experiments. So that makes us hopefully have relatively stable conditions in future as well. We will, as mentioned, change the dewatering device. We will collect more data with the primary sludge and collect more PHA also for our partner NaturePlus in order to check the suitability of the PHA material for the end products. And afterwards, we start to investigate different industrial substrates as well. And all these information should give us a base for dimensioning parameters and operational hints. So let me shortly announce one more event within the Green Week. For those who are interested, we have on June 7th on 2 o'clock in the afternoon an online event. We wanted to have a real visit of our pilot plant. That's not possible. So now we have a film which you can see with some presentation advanced and some discussion afterwards. So who wants, you're more than welcome to join us at the 7th of June again. So that's from our side everything. Thank you, and feel free to ask questions.
Okay, thank you very much, Heidrun and Rosalia, for your nice presentation about the PHA pilot. And then there's of course time for questions. I already see one hand raised for a long time, but I don't know the name because it doesn't say full in the screen. Johan, I'm not sure. Do you have a question? Apparently not. Anyone else who has a question for Heidrun or Rosalia? Well, I do have one question, because you told already, Heidrun, that the yields of PHA currently at the reactors are still rather low. So what would you focus on the next step? The first things you would like to change to increase the yield of PHA in the pilots?
What we want to investigate more closely is the selection process. So what is the role of the bacteria in the system? The results I showed you here are with just 1 week selection time for the bacteria, and then all these bacteria are used for the PHA production. And we want to install also another process with long-term selection, and then use just part of these bacteria so that we can have a stable population, and hopefully these bacteria are more effective. And in parallel, we work also in the lab on investigating more closely the biocenosis, and want to figure out which bacteria play the main role in the system.
Okay. Thank you. And maybe one other question: what do you think is the biggest challenge to make PHA production commercial in the end?
I think the biggest challenge might not be the technical challenge. We have some technical challenges, but I'm pretty sure we might be able to overcome them more or less. So the biggest challenge, at least for the German situation, is actually that the operators of sewage treatment plants are, well, not really the right persons to sell this material and to set up the whole process chain. And I think we have to find solutions for that. Who can do that, who can support, and so on.
So you need a third partner in this case who was more accustomed to deal with this. Yeah. Okay, I would have to agree. So thank you very much. And then, considering time, I would like to go to the next presentation, which also is a duo presentation. Good to see you, Coert, that you were able to join in time. So the next presentation will be about pyrolysis of cellulose, which is also a second pilot in the WOW projects. And this will be a presentation by Coert Petri, who is a senior policy advisor at the Water Authority, Waterschap Vallei Veluwe in the Netherlands. And there he's involved in new developments related to resource recovery from sewage. And he will be helped by Mark Lacroix, who is a process development engineer at Pulsed Heat, which is a company that develops and implements sustainable solutions for all kinds of residual streams. So I would like to give the word to you for your presentation about pyrolysis of cellulose.
Thank you. Well, I will start. I'll try to share my screen. Is it visible already?
Yes, it is. Yeah.
Okay. At the beginning, excuse me. Yeah, I just got my vaccination, Moderna, half an hour ago, so I might fail but then Mark will take over, and Mark will take over anyway halfway. We'll tell you something about the cellulose pilot plant. All toilet paper ends up in the sewer system, and the sievings we can take out, and then we have a cellulose recovery, and that can be turned by pyrolysis into biochar, bio-oil, and acids. And that's what we intend to do with this pilot, which is about to start. From toilet paper, I already explained sewage. Well, the wet part in the hole is the cellulose sieves, the screens where we take out the cellulose. I will tell you something about that. And after that, there's the thermal part and the pyrolysis part and the drying. And Mark will tell about that, and that turns in these three products, which we will explain later on. The biochar can be turned into activated carbon. That is our intention, and we hope that the activation will turn out to be profitable. These three partners are involved: Certec, Pulsed Heat, and Waterboard. Here the process. So first the sieves on the left here. These I will show them later on. Then the dewatering up to 45–50% dry solids. Then we dry it, and then we make pellets from it, and those pellets are dried again up to 90% dry solids. And then we go to the pyro flash reactor, which is short, and then with high temperatures we turn it in three fractions: the acid fraction, the bio-oil fraction, and the biochar fraction. The screens, the sieves, well, they are placed after the core screen because we want to get rid of the bigger parts. And then we'll take out the cellulose screenings, which consists of about 3/4 of toilet paper and all kind of proteins, fats, and some ashes, the other 25%. Well, in the Netherlands, these screens are more and more placed in the wastewater treatment plant, and just to reduce the load of the plant, so you can avoid to extend the plant. And these sieves you see here, they both can handle 300 cubic meters per hour, and they can handle 25% of the wastewater treatment plant of Ede, which is 300,000 PE, so they can cover 75,000 PE. The dewatering press, so we press it to 45–50% dry solids. And here you can see the sieve. It's a belt kind of sieve which turns around. And the sievings are by air are taken off here over here. And the water falls through and goes back to the wastewater treatment plant. It's a 350 micrometer mesh, but because there is this coating on the left side where you have the coating of the cellulose, you also take out smaller particles. Well, in the middle you see the screenings, and after the dewatering, it's already quite dry. You have this 50% dewatered cake. From here, I would like to give the word to Mark. Mark, you will tell me when to go to the next slide.
Yeah, sure. Thank you, Coert. But we can go to the next slide.
Yeah, the drying section you see now?
Yes.
Next slide. You don't want to tell anything about this?
Oh, yeah, I can also do that in the next slide. Oh, huh? Oh, maybe there's something wrong because I'm already at the pyrolysis slide.
Here the drying section.
Ah, yeah, there it is. Okay. So after material has been dewatered, the cake is transported to the other section of the hall. And in this section, the first step is to dry the material. and to make pellets of it. We have several machinery in place for this. First off, we have a falling curtain dryer, and I just noticed that the patent holder for the dryer is also in session, but that's more a side note. The cellulose is transported with a screw to the dryer, and the dryer is fed with a flue gas stream, and that flue gas stream is coming from a pyrolysis and propane co-combustor. So the dryer basically consists out of two sections. First, there's a flash section, and there the bulk of the water is evaporated. And then there's a section where there are several paddles, and the paddles are throwing the material in the air. And the material can dry better because of the high mixing with flue gas. And as you can see at the bottom, there's a picture of the fluff. That's the material coming out of the dryer. And it's probably at 60–65% dry solid. The fluff is then transported to the pellet press, and in the pellet press we obviously make pellets of it, and the pellets are transported to a deep dryer using a belt conveyor. And in the deep dryer there's a side stream of the flue gas from the co-combustor, and we mix it with some air to reduce the temperature, and then we have a pellet bed, and the hot air is coming through the pellet bed to dry it further to 90%. Okay, we can go to the next slide. So all this drying and pelletizing of the cellulose is to make it suitable for the pyrolysis section. So what is pyrolysis? Pyrolysis is a thermal treatment for organic material. Basically you heat the material without any oxygen, or with a low oxygen content. And then part of the material will degrade, and a volatile fraction, gas fraction, leaves the material, and that can be condensed into various fractions. So there's also a bottom product, and that will be a biochar. In this reactor that we're using, we have a temperature gradient of up to 900 degrees at the hottest point, and then going to 200 for the gas fraction. So the advantage of this high temperatures that you also destroy pathogens, and there's a degradation of toxic components. But this also has to do with our starting material. The cellulose coming from wastewater, it also contains quite a large amount of unorganic material, for instance, sand and other metals that are present in the wastewater. And then depending on the products you want, the flash pyrolysis has a higher yield for bio oil compared to the biochar. We can go to the next slide. There it is. So let's take a look at this pyrolysis section. So I've indicated the different steps with numbers, but we have a pyrolysis reactor, of course. There the pellets are stored, and we have a heat source for the pyrolysis reactor. This is a gas burner. It's a small burner, like 4 to 40 kilowatts, and it produces a flue gas stream of 900 degrees, and which we use to heat the pellets. And then the mechanisms I just described occur. So this leads to a biochar, which we remove at the bottom, and a stream of volatile components. And those volatile components are led to the separation section. And there in the separation section, we're able to condense components, and we get two liquid streams versus a bio oil and a pyroligneous acid. Further, there's a stream of non-condensable components, and they also still have an energy value. And we transport it back to the pyrolysis biogas co-combustor, and there we combust it, and we use the heat for our two dryers. If we could go to the next slide. Yeah. This would be a good way to look at the different products in depth. So on the left, we have the cellulose pellets. So this is our feedstock, and then using the pyrolysis process, we will be able to derive 4 products of those. So first will be the biochar. So the plan is to use the biochar at the wastewater treatment plant. So first, I'll probably tell this in depth at the next slide, but basically the activation makes sure the micropollutants from wastewater will be able to be absorbed better, and then you can remove the micropollutants from the effluent. Further, there will be a bio oil. This is a high energy dense oil, and due to the separation mechanism in this machine, the oil has a low acid content and a low water content. So both these things, they increase the heating value of the oil, and they also make it more friendly for burners. Further, there's this acid fraction. We're planning to use it on the wastewater treatment plant, and can be used to enhance the denitrification and for the bio process. And further, there's the pyrolysis gas. And as I just mentioned, we are going to burn it in the co-combustor, and then we can use it to supply heat for the dryers. If we could go to the next slide. Okay, the active carbon. So for the water, the goal is the goal of the biochar is to produce and upgrade it to activated carbon. This can be done in several ways. So you have a thermal process for this, a chemical or a biological, and ranging on the process you use, there's certain investment costs, certain operation costs, and also leads to a different microstructure for the carbon. So you can see a picture of the carbon at the right corner, and if you zoom in, there's a really big, there's a sort of microstructure, and the type of microstructure depends on what kind of particles will bind easily to it. For instance, hydrophilic groups or aromatic groups. And basically you have to design your carbon for the material you want to use to remove it from, to remove. If we could go to the next slide. Since this will be one of the goals for the project, the removal of micropollutants from effluent. So in this whole process, since there are several steps, there's also quite a lot of variation in what would, not variation, but quite a lot of variables that would influence the removal. So you have different effluent qualities. If there's a first flush, you can get more sand, you can get more different minerals, you could get more fat. Then the pyrolysis process, the quality of the feedstock is obviously important, the temperature and the residence time. And then on the activation, you also have several routes, residence time and temperature. And then obviously also the quality of your effluent and the amount you want to remove. So there's a lot of optimization possibilities for this installation, and also reduction of the energy needed for the installation, and tweaking for the desired products. For the next slide, please. This is also my last slide regarding to time, but so a wastewater treatment plant is a stable source of biomass, and having a stable source of biomass is important for a producer. So you also get hopefully a stable source of biochar and oil with minimum variations in it. So this also gives you the possibility to create your own activated carbon then, and then to replace a fossil-based activated carbon. And when we get some more data on the process, we can also start with some energy reduction tests or components, adding them, for instance, using biogas instead of propane, or changing the heat source for different components. And also the impact of the fine sieves on the wastewater treatment plant has to be evaluated. For instance, we'll be able to reduce the amount of sludge with it, and probably also reduce the aeration needed. And in the next few weeks, we are going to start producing our own bio-based products. So it's going to be an interesting few weeks. Yes, next slide, please. Yes. So before I would like to ask if there are any questions or suggestions, I have a remark based on the previous presentation. I noticed they were also telling about their active learning efforts. So I'd also like to make use of that opportunity. So on the 4th of July, there's also an active learning visit as part of the Green Week for this pilot. So we'll also be discussing this more in depth. Then are there any questions?
Okay, thank you, Mark and Petri. Coert. I just always mix them up and somehow, I don't know why. I see one question from Alexander in the chat. Alexander, can you ask the question yourself?
Yes, of course, that's possible. It was a question for Coert indeed. You told about a sieve with a capacity to screen the cellulose about 75,000 PE, and that was installed or tested at a sewage treatment plant with a capacity of 300,000 PE. So basically my question was, why was chosen for that 75,000 PE capacity sieve?
Yeah. Well, bigger plant would have come more expensive. So it's quite a big pilot plant already, and we decided to build it this way. So pyrolysis reactor have good capacity.
Yeah, so it's not the maximum size of a sieve. A sieve can be even a higher capacity, but it's just. And then my follow-up question would be, how do you handle the overload? So I can imagine that average daily is not a 300,000 PE each day, of course. But how do you handle the overload? How does it work in practice?
Yeah, the rest we bypass. So at rainy days we bypass, and there's also a primary sedimentation tanks even. So it's yeah.
Yeah, clear. Thank you.
Oh, thank you very much, Alexander. Are there any other questions for Mark or Coert? No, I see someone else talking. Here's someone else talking, but not a question. I was wondering, I do have a question, because there's also other applications of cellulose which are possible. So why did you choose in this case for pyrolysis?
Yes, well, we have to remove pharmaceuticals in the coming years, and we are looking for green sources of activated carbon, because the fossil CO2 footprint of activated carbon is not so good. So we prefer to do this way. So we can combination of both worlds.
Yeah, indeed. And I saw you also use the acids you could probably apply in the sewage treatment plant as well, if everything goes well. So then you have a multiple use of the products within the whole sewage treatment plant.
Yes.
Okay.
We can avoid all kind of end of waste problems if we can use it in our own plant. So that's more simple.
Okay. Clear. Thank you very much. Well, considering time, I would like to go to the next speaker. So the last speaker before the coffee break.
Jappe?
Yeah.
I saw raised hands by Michiel
Oh, sorry,
Bos.
that's what I completely missed. That's when.
Thank you very much. Thanks, Coert and Mark, for the presentation. For Mark, I wonder, are there any disadvantages from medicine residue in your bio-based product?
No, I think not, because we also have in the process reactor heat treatment. So it will be heated up to 900 degrees centigrade. So most pharmaceutical compounds will also decompose at that temperature.
Okay, thank you.
Okay. Well, once again, thanks for the presentation. So then we'll go to our next speaker, which is Luca Loreggian. I'm not sure if I pronounced it correctly, probably not, but I give it a try. Who is an associate researcher at the University of Applied Sciences of Northwestern Switzerland. Like to visit it at some point, and he is looking into the use of granular activated carbon for the removal of micropollutants, and today he's giving a presentation which is related to the project nextGen. So I will give the floor to you, Luca.
Yeah. I'll share my screen. Can you hear me?
Yes, I can hear you,
okay.
And I can also see your screen.
Okay, perfect. Okay. I think my presentation is a very strong introduction from Mark and Petri. I think we are working kind of going on the same direction. Here I will indeed talk about production, manufacturing of granular activated carbon from sewage sludge. So here we are looking at not primary sludge, but secondary sludge. This is a part of nextGen. nextGen is European a project funded by European Union's Horizon 2020 program, where we're looking at a circular economy approach for the recovery of water, material, and energy. And within nextGen, we are working on one demo case based in Altenrhein on the Lake of Constance. And within this demo case, we are working on recovery of phosphorus, nitrogen stripping, and production of granular activated carbon, which is the topic of my presentation today. So maybe a few words about the sites. This is a wastewater treatment plant with the capacity of treating 100,000 person equivalent and 300,000 person equivalent just for the sludge treatment. And it is here based on the Lake of Constance. You can see on the border between Germany and Austria. Altenrhein, as all that a typical wastewater treatment plant has, but also a step for micropollutants elimination. This is in operation now since quite a few years, and it consists of it's a two-step process, and consists of ozonation first, and then adsorption on granular activated carbon. And so this is how the process trains looks like. After the secondary clarifier, they have a sand filtration system, which is feeding an ozonation plant. It's a 2 lines plant with 2 points of dosaging for ozone dosage. And the effluent of that goes into the a fixed bed contactor with granular activated carbon. And the goal of the operation is to eliminate 80% of the 12 micropollutants indicators that have been selected among all the possible micropollutants you can have in wastewater. And so in Switzerland, we are looking at the sum of these 12 indicators and how much we can remove from the inlet to the outlet. And when you achieve 80%, that is enough for the requirement. And so since as you heard from Mark and Petri, granular activated carbon is a very efficient process for micropollutants elimination, but also a very high CO2 impact. And so one of the question we had within nextGen is whether we can produce GAC from renewable resources that would lower down the impact of the process. In fact, two goals. We have two goals. One is to manufacture GAC from renewables that has a similar performance as what you can buy on the market. And the second goal would be to actually test these products and for the elimination of micropollutants. And so we structure our work in three consecutive phases. We went through a very long and time-consuming phase where we've been testing different conditions of pyrolysis and activation, both on lab scale and a pilot scale. We have been generating a lot of samples, and we've been characterizing all of them, trying to identify what is actually the best the best products between all these samples that we produce. We then went to a very long production phase. We could generate two types of GAC, and now we are actually already on the third phase, which is the piloting of the GAC filters for the removal of micropollutants. We've been running the pilots now for about 6 months, and we hopefully can run it for a bit longer. As Mark said, you can produce, there's so many different conditions that you can use to generate GAC, and you can vary the temperature of pyrolysis and activation. You can vary the type of activating gas that you are using and the residence time in the reactors. And these are actually the three conditions, the three parameters that we have been investigating. And on top of that, we also been looking at another renewable source, another source of carbon, that is the cherry pit stone that we have available here in the region. So we been investigating all of these conditions. And we also characterize all our samples. We used a battery of measurements. Some of them are standardized methods, and some other methods we developed by ourselves. We looked at the yield of production, so how much feedstock we're actually consuming to produce a certain amount of GAC, and their ash content. We looked at particle size distribution, and we look at density and hardness. These are very important physical properties of your GAC. One tells you how much material you can actually pack in a certain volume. And the second one, the hardness, will tell you how long or how likely is that your material will stand in the condition of your filters, so for a very long time. And the two other methods that we use are we measure specific surface and porous size distribution, as well as the capacity of these carbons to absorb micropollutants. Maybe I'll go I really want to focus on the result of the pilot, but I'll still want to show you how much conditions of pyrolysis and activation can impact on the results, on your final result. So this is an example from a thermogravimetric analysis where we've been looking at the ash content of two different materials. One is a GAC produced from sewage sludge, and the second one here, the three last bars are GAC produced from cherry pit. So depending on the feedstock that you're using, you will end up with a very different type of material. In this case, we see that GAC from sewage sludge is a very low amount of carbon at the end and a very high amount of inerts. Vice versa, the cherry pit GAC is a very high amount of very high concentration of char. And as well as density is another parameter that we see changing a lot depending on pyrolysis. And for example, depending on the amount of activating gas that you're using, you'll see a difference in density, and also depending on the feedstock. So these three points represent GAC from cherry pit activated with different amount of steam or water, and how does the same condition of activation do not impact on the properties on the density of a sewage sludge. We also see how much sewage sludge GAC is higher as a more dense material than cherry pit, and this has a very important implication for the production, the use, and the operation of your filters in the end. So after this long phase of testing in the lab, we could identify two types of materials that we think are feasible to be used in a pilot, in a filters. One is a GAC from sewage sludge that we activated with CO2 and at 800 degrees. The second one is a GAC from cherry pit activated with water and 900 degrees activation. So we were quite pleased with the hardness of this GAC from sewage sludge. This is a method, a standardized method to measure hardness, and it's the harder material we could produce, and it's quite close with the hardness of materials you can find on the market. So this is our reference materials. Typically, commercially available carbons has a hardness of higher than 90%. So we are quite happy with this one. Vice versa, the second carbon was a more brittle material, but still a very good adsorber. So here I'm showing you the adsorption capacity using SAK. SAK stands for spectral absorption coefficient, and is often used as a proxy for the adsorption of micropollutants. Is not a perfect proxy, but somehow give you an indication of how much that type of carbon can absorb micropollutants. And so with these two materials, we went into production and set up our pilot experiment. This is how our pilot looks like, and it is installed at Altenrhein and is fitted with the effluent of the sand filtration of the plant. It goes into an ozone reactor, and then we have three parallel lines with our GAC. One being the commercial, this is our reference experiment, and then the two GAC that we produce from cherry pit and sewage sludge. And the sand filtration would be a control experiment. And we have been operating this system at quite a standard condition, so quite high ozone dosage and a typical residence time of 20 minutes. And so an empty bed contact time of 20 minutes, at least for the first period of operation. It will go quickly through this. I just want to point out, maybe show you how much density of your material can impact on the performance of your filters. We have a very light material from cherry pit and a very dense material from sewage sludge, and which means that if you have same height of your filters, you can pack a lot more GAC from sewage sludge than from cherry pit, and that will strongly impact the adsorption capacity of your filter. So we have been monitoring our plants using SAK and DOC as a proxy for micropollutants because they are fast and cheap, but we also been measuring micropollutants. And we actually focusing only on 12 compounds, the majority of them being on the list of the 12 micropollutants indicators that are for Switzerland regulation, for the Swiss regulation. And so maybe the first data set I'll show you is the elimination of micropollutants over time here in bed volumina. So you have the percentage of micropollutants elimination of each single compound. And this is the result from our control system, so the GAC with a commercial carbon. And in yellow being the elimination by the ozone, and in black the elimination by the GAC. So for most of the compound, this is what you would expect from a commercially available carbon, and very high elimination, especially in the first phase of operation. This is 8,000 bed volumina is not very long time for a GAC filter that can go up to 30,000, even 80,000, so 10 times longer than this. So this is what the performance that you would expect from a GAC filter. And here now the first result from our renewable carbon, not as satisfying as the first data set I would admit, but for some of the compounds, we actually see a quite high elimination. That is the case of amisulprimide, hydrochlorothiazole, benzotriazole, citalopram, and also the sartan compounds, which are typically not very like strongly and not very easily absorbed. And unfortunately for the cherry pit, actually the results were even worse. They do not perform as well as the sewage sludge GAC. But nonetheless, this for us is still a promising results, because we could produce renewable GAC that can absorb. Now the question is whether these compounds actually need a different type of operating conditions. So maybe the standard condition that you would use for commercial carbon, they're not fit. They don't fit with this type of GAC. If you sum up all the micropollutants and you look at the total elimination, you can see how ozone on average allow you to achieve about 20% elimination. But is and then the rest would be eliminated by the GAC. So, and how quickly the commercially available carbon actually are decreasing in terms of absorption capacity, and that really suggests that the operating condition might not be they're not optimized yet. And this indeed is our second phase. We're now working on to change the operating condition, and we'll be operating the system with a higher empty bed contact time. So a higher empty bed contact time means that the system will be able to, the water in the system will sit longer in the filters and allow longer time for absorption. This, in principle, will increase the absorption capacity of the, also better the efficiency of the absorption. I'll go this not so relevant, and I'll skip to the conclusion. And so my conclusion for until now is that yes, we could manufacture 2 GAC from renewables resources. That is a promising result. I mean, there is the potential to use this, especially sewage sludge is a good feedstock to produce GAC. And we could achieve a significant elimination only by GAC absorption, but this is still not enough to achieve the aim of 80% elimination that is required by the law. And that means that we need a better optimization of the filtration condition. And this is why we are now be looking at the higher empty bed contact time, as I said. So that's the end of my presentation. I'll take the opportunity to thank everybody that's been working on this project. my colleagues at University of Applied Science, and all the people involved from the wastewater treatment plant. And with this, I would like to thank you for your attention and happy to take your questions.
Thank you very much, Luca, for a very nice presentation. Are there any questions for Luca?
Yeah, look at this. Look at the chat. I heard a lot of. Okay.
I don't see any hands raised, and I don't see questions in the chat. Well, I do have a question, because you looked at the difference between the GAC from cherry pits and from sewage, and they had different properties, I can see, and different densities. Are you also looking into mixing them both? Would you think that could be an option? And do they have different characteristics in which micropollutants they remove, or is it the same?
Yeah, they have pros and cons. So cherry pit has a very high surface area, so has the potential to absorb much more materials, much more micropollutants. But the problem with cherry pit is the density, and that's why I'm thinking that sewage sludge is just a better material. And the drawbacks of using sewage sludge is that there's a very low content of carbon. So we actually filling filters with a very tiny amount of materials that is actually contributing to absorption. So mixing them is a possibility, but I think we will also be looking at different type of feedstock in the future.
Thank you. Could you unshare your screen, Luca? Because now I'm looking at myself, which usually I only do in the mirror in the morning. Sorry. So I see 2 hands raised at this moment. I see a question from Sietske.
Okay.
Yes, thank you very much for your interesting presentation. I was wondering, what kind of treatment do you use for your sewage sludge before the pyrolysis phase?
So the sewage sludge is being digested and then dried. Yeah, so it comes as a pellet, actually. And this is a very convenient process, because it's basically already granulated. So we don't need to do anything, really. There's a very low water content, and it's ready to go. We actually sieved and removed some of the finest fraction, which would actually contribute to loss of material, and that's the only thing we do.
Okay, so it's dewatered and digested, and then it's ready for pyrolysis.
And I have to mention that is co-digestion, so there is some feedstock in the anaerobic digester. They have some like food waste material as well that goes in, so it's not just sewage sludge.
Okay, thank you very much.
Yeah.
Okay, thank you. And I see one more hand raised, which is from Rosalia. Rosalia, can you ask your question?
I have a question, because you did mention looking in for the functional groups on the biocarbon, so you only concentrate on the surface area and the porosity, but sometimes the functional groups could help to compensate the.
Yeah, definitely, but we didn't look at that. We probably been measuring pH, but we didn't look at the functional groups. Yeah, thanks.
Okay, thank you very much again for your presentation, Luca.
You're welcome.
And then for now, I'll briefly share my screen. So we have a short break now, so please come back after the break, because we have some nice presentations left. So we have 2 more presentations from the WOW, but we also have a presentation from Deeppurple and from Nereus. So I suggest, since we're a bit later, we will have a coffee break until 10:50, and then I hope to see you back again for the next presentation. So enjoy your coffee and see you back in about 8 minutes. So welcome back, everyone. I hope you all had time to get yourself a coffee or a tea. So I would like to, considering time, continue with our next speaker. And our next speaker is Victor Monsalvo, who is head of the eco-efficiency area in the Innovation and Technology Department of Aqualia. And he's also the coordinator of the project Deeppurple. And today he will give a presentation about solar biorefineries, which is part of this Deeppurple project. So Victor, I would like to give the word to you.
Yeah, thank you. Thank you very much. Good morning, everyone. And thank you for giving us the opportunity to present today our lovely Deeppurple project. And it's going to be just 15 minutes of bottom-up information of the project and the results that we have obtained so far. I hope now you can see the full screen already.
Yes, we can.
Wonderful. So this is probably a new concept for you, because in Europe, this is the first initiative that is carried out around the use of these bacteria. The concept is based on biorefineries, where we use phototrophic bacteria, and they're great because they can transform bio-wastes into different products. They are phototrophic. This is why we call solar biorefineries, because we extract these bioproducts from bio-wastes. They have different metabolism. They are phototrophic, but they can use in a different way. They can be phototrophic, they can be chemiotrophic, heterotrophic. So we can play a little bit with their metabolism, and then we would have a very flexible and adaptable plant. This is the outline for today, the index, a little bit of background, why we created this project, which is co-funded by BBI, basically to solve or to give another opportunity to solve the problems with bio-wastes valorization or management. As you know, the European Commission has established this target by 2030, and more than 65% of the municipal solid wastes should be reused or recycled. And as you can see here, we should increase the greenish bars up to 65%. Only Germany has reached this value, but the rest of the countries have to do a bigger effort to cope with this threshold value. And at the same time, and with the same view, the target by 2030 is to reduce by 10%, only 10% of the municipal wastes should be landfilled. And again, we have a tremendous challenge in front of us. One of the opportunities is to transform these bio-wastes into bioresources. How we do with this Deeppurple project? Well, the main goal in a simple sentence is to have the demonstration in Europe, the first demonstration worldwide actually, of a versatile, integrated, and flexible multi-platform biorefinery. What does this mean is we want to have this platform for the transformation of bio-wastes. It's flexible because we can accept in our inlet different bio-wastes, mainly the organic fraction of municipal solid waste and the wastewater. It's a multi-platform because we can create multiple bioproducts depending on how we operate the photobiorefinery. And finally, the main products that we want to obtain with the process is the slow-release fertilizer, biofuel as biomethane, cosmetics, self-healing construction materials, and bioplastics, both for biopolyesters and packaging. The main core solution or technology of the entire Deeppurple solution is this PPB. PPB is the acronym for Purple Photobacteria Photobiorefinery. This is the most innovative one. We collect these two main streams, the organic fraction of municipal solid waste, which are preliminarily treated by hydrolysis, thermal hydrolysis, before entering into the photobiorefinery. Or we can go through the anaerobic digestion. Then when we obtain the biogas using methanotrophs organisms via fermentation, we can obtain ectoine. Ectoine is a cosmetic compound, very costly and sun protector compound that is used in the formulation of biocosmetics. On the other side, we co-treat simultaneously in the photobiorefinery wastewater, where firstly, we can recover cellulosic material, as you have presented today, this morning, the WOW project, or the liquid fraction, it enters into the photobiorefinery to obtain, finally, biofertilizers, slow-releasing biofertilizers or packaging materials. Once we obtain or recover the cellulosic material after downstream, based on the production of carbon nanofibers and then saccharification, the production of sugars, a new generation of sugars to obtain biopolyester, we obtain this biopackaging, or this cellulosic material can be used to obtain composites together with PHA and bacteria to obtain self-healing materials for construction. This is the global idea. In 2 minutes, I summarized the global idea of Deeppurple. How is the methodology of our project? We have 3 phases. The first one is the optimization and upscaling of all the processes included in the Deeppurple solution. We have finalized this phase 1, and we have already entered in phase 2, which is the design and launch of the demonstrators. We will construct 2 demonstrators in Europe working as photobiorefineries. And the third phase and last one before finalizing the project by 2023 is the validation at industrial scale of the final products. In this final phase, standardization activities are included for the acceptance of these bioproducts by our end users. For bioplastic or for packaging, for example, we are working with Novamont and Naturplus. For the chemical precursors for the cosmetic industry, we work with R&B, which is a producer of cosmetics. The slow-release fertilizers are used by Roulier in France, and the self-repairing materials for construction are used by cement industries. How is our consortium? We are 14 partners from 6 countries. We will create these 2 demonstration sites, and our logistics is we have 2 centers, main centers, so we have these photobiorefineries, and once we have intermediate products, these intermediate products are transported to the factories of our partners to obtain the final product in a decentralized mode. More information about the demonstration sites. The photobiorefineries will be based in the south of Spain, in Linares, where we have a lot of sand there for the photobiorefinery, and the second one is being defined right now. Then, when we have these transformation sites, the photobiorefineries, then the intermediate products are transported to the production sites, which are distributed around Europe to have the final products. Main figures, sorry to try to summarize 2 years work in just 1 slide, but I think that it's very simple to understand where we are now. As I told you, the main core technology is this PPB photobiorefinery, and you can see here the pilot plants that we are running in Spain. And here in this picture, you can see the largest anaerobic photobiorefinery worldwide. It's still a 30 cubic meters photobiorefinery, a previous step to have the demonstrator in the south of Spain. Another technology is involved in the whole Deeppurple process. is the hydrolysis of the organic fraction of municipal solid waste. You can see here the picture of the pilot plant running in Madrid, where the municipal solid waste from the city of Madrid are treated by this technology. And then once we produce the biogas after the anaerobic digestion, this biogas is treated by these pilot plants where we have methanotrophs, and these methanotrophs transform methane into ectoine. These are the main results: 95% efficiency in the transformation of methane into ectoine, and at the end we extract this product in a 4% dry weight, which is available for commercial use. If we continue with the rest of the bioproducts, fertilizers from this PPB biomass, you can see here how it looks like after the collection of the biomass from the biorefinery. It's been tested by Groupe Roulier in France, and they are very happy with the results. They are using and comparing this fertilizer with commercial ones, with different cultures like soybean, maize, etc. And the production of the plant so far has been increased by 32-35%. If we continue with the biopolymer section, these products, we are looking for a new generation of biopolymers, basically PHA, and our partners have developed a downstream processes for the extraction and purification, concentration, and drying to obtain a commercial product, which basically is 98% purity of PHA. The global recovery process efficiency is 72%. When we obtain a PPB biomass, a phototrophic biomass, with a concentration between 30, 40, even 50% of PHA has been obtained so far as maximum. A good point to highlight is that these materials, this PHA material, has demonstrated to have excellent mechanical properties, but more relevant is the biodegradability. It's 20% faster if you compare it with commercial available materials. If we continue with the construction, self-healing materials construction, the University of Brunel, they are developing this material that recently they have identified that they have internal compounds together with bacteria, together with PHA, and they are obtaining calcite and other compounds inside that are good news to have a self-healing material. And then last is the recovery of cellulose from wastewater in Deeppurple, where this material, cellulose, can have use in the pulp and paper industry, but also the carbon nanofibers that are recovered are also treated and downstream, in this downstream with our partner Itene in Spain, to have these biopolyesters after fermentation and so on. Maybe it's a little bit complicated if you have in one picture all the possibilities that we have in our flexible concept. But if you decide to obtain a certain compound, the scheme is much simpler than that. Just as one example, if you decide to have your photobiorefinery working to obtain PHA biopolymers or fertilizers, it's as simple as that. We will have this photobiorefinery based in a wastewater treatment plant where we would have access to the domestic wastewater, plus we have to be connected with the plants where municipal solid wastes are managed. After the reception, selection, blending, and hydrolysis, thermal hydrolysis of the organic fraction of municipal solid wastes, this hydrolyzed is fed into this photobiorefinery together with the domestic wastewater, and then we obtain the PPB biomass, and after downstream, which would be the final product at the wastewater treatment plant, and then this intermediate product will be transported to the final production sites to obtain a PHA or the fertilizer. Much simple, with just one or two goals than if you see the global solution. I think that this clarifies your idea about the Deeppurple implementation. And then just a little bit summary, how are the goals and challenges that we are facing in Deeppurple is to construct this solar, 100% solar power plant to obtain these bioproducts. But at the same time, our effluents have to fulfill with the standards for the discharge into the environment, both for wastewater and the hydrolyzed fraction of the municipal solid waste. This is the roadmap, how we have upscaled the process since 2018. We started by 2015 with lab scale systems. Then we have it by 2018, we started to work with a pre-pilot system. You have the capacities there. Then after 2 years work, by 2020, we upscale the system for this pilot scale, which is the system that has been already running for almost 2 years. And this year, we will have the first demonstration scale plant in the south of Spain. So we hope to have results very soon to share with you. These are the main targets by the end of the project, the total capacity that we have to fulfill after these 4.5 years project, more than 400 tons a year of organic fraction, more than 400,000 cubic meters a year of wastewater treated. We want to obtain to reach this yearly production of bioproducts around 400 tons. We would save these tons, more than 10,000 tons of CO2, and reduce the organic fraction of municipal solid waste that finally reach landfills. Thank you very much for your kind attention.
Thank you very much, Victor. And I would like to ask the audience if there are any questions. I see a hand raised from Coert.
Yes, I'm very impressed with all these projects together in Deeppurple. And I'm especially interested in what's happening in the photo biorefinery. What's happening there? Is that the algae reactor or what's happening there?
Yeah, excellent. Thank you very much for your question. Actually, the design is pretty similar to algae ponds or raceways, right? But there are some differences in the design. We can work, if you compare with algae ponds, we can work with a more higher column of wastewater, and we have to filter the solar radiation because these photobacteria operate with infrared. This is part of the patent that we have. This filter that you saw on the top of the reactors, we filter to have infrared radiation. And then we only mix and put together the wastewater and the hydrolyzed organic fraction of municipal solid waste together with the biomass for a certain time. Yes, mixed. And then we have secondary settling tanks because these bacteria settle very well. It's easy to separate and to obtain this PPB biomass after this.
Okay, thank you. Interesting. Absolutely.
Okay, thank you indeed for a very interesting presentation, Victor. And well, considering time, if you have any more questions, I'm sure you will be able to answer them in the chat if people put them in the chat. And then I would like to go to our next presentation, which is a presentation from Zuzana Dedova, who is a postdoctoral researcher at the University of Luxembourg, where she focuses on the fate of environmental pollutants and their bioremediation. And today she will tell a bit more about the pilots that they are running on biodiesel production from sewage. So, well, the floor is yours, Zuzana.
Thank you very much, Jappe, for your introduction. I will share my screen. Okay. So, good morning. My name is Zuzana Dedova. I'm a postdoctoral researcher at the University of Luxembourg, and today I'm going to speak about biodiesel production from urban sewage within the Interreg Northwest Europe WOW project. Beside myself, let me introduce you also other people from the lipid pilot team. Marie-Louise Uwizeye, which was mostly representative for the lab scale study. Fernanda Muniz-Sacco, our master student, now helping very much with the lipid pilot, and senior researchers Silvia Venditti and Professor Joachim Hansen. Then we have Arsu Arimi from Remondis on board, and also Amélie Léger from Sivom Delazet, the wastewater treatment plant operator where our lipid pilot is located. So lipids, fat, oil and grease, or FOG, are present in the municipal inlet sewage at relevant concentrations. When calculated to the population equivalent, it is about 35 to 50 grams per day. From this amount, 45% of the lipids originate from feces, while 55% from kitchen waste. Lipids are present in both liquid and particulate forms. Most common lipids in the sewage treatment plants are oleic, palmitic, and linoleic acid, all known to be suitable for the production of biodiesel. When it comes to the long-chain fatty acids, meaning carbon chains longer than 12, the concentration varies from 20 to 500 milligrams per liter, with an average estimated around 150 milligrams per liter. Current handling of lipids. While the particulate lipids are removed in the sand and grease trap and then disposed at high costs for the operators, the dissolved lipids get partially degraded to carbon dioxide. Although being less responsive to biodegradation compared to other organic substances such as sugars or amino acids, lipids are readily removed in activated sludge, or they are being embedded in the biomass. Then we have two possibilities. Either in the large wastewater treatment plants, the activated sludge is digested and biogas is produced. So we have the energy production, which is really nice. But on the other hand, the other wastewater treatment plants without the digester, the sludge where the lipids are accumulated is actually disposed. So valuable resources are being lost. So we are losing a lot of the lipid potential currently present at the sewage treatment plants. Starting from the initial calculation of the amount of lipids in the sewage inlet per population equivalent. So 50 grams per inhabitant per year means 18 kilograms per lipids per inhabitant and year. In Northwest Europe, we've got about 250 million people being currently connected to municipal sewage treatment plants. Therefore, the total load of lipids in Northwest Europe is estimated to be about 4.5 million tons per year. We are not talking about the industrial wastewater treatment plants, which may, of course, add substantially more. So impressive potential for biodiesel production is really seen from wastewater. Going a little bit back, the first work on biodiesel production from urban sewage was already published in 2009 by an American group of Mondala et al. The production of FAMEs, fatty acid methyl esters, meaning biodiesel from conventional sludge, primary and activated sludge, by chemical transesterification was about 10% of dry biomass. Back in 2009, the estimated costs for production of biodiesel was about 20 cents per liter of biodiesel. Sustainable production of renewable and economically feasible biofuels is nowadays really a hot topic globally. Understanding of resource limitation, land use or water scarcity for first and second generation biofuels, mostly from food crops or non-edible biomass residues, gave rise to the third generation biofuels produced from non-edible feedstocks such as microalgae, bacteria, yeast, fungi. Use of biomass known to accumulate long-chain fatty acids is possible and most likely will increase the yield and thereby decrease the costs for biodiesel production. Here is background for our study. So far, microtrix was only associated to solid liquid separation problems, causing foaming and bulking in the activated sludge. Microtrix is one of the lipid accumulating microorganisms that could contribute to actually supply future energy demands. Sewage treatment plant operators adopted different solutions to control the overgrowth of this bacterium. Use of selectors to promote growth of flock forming bacteria has been of common practice in recent years. These selectors, however, can also be used to promote growth of microtrix when favorable conditions are selectively ensured. This was our lab scale study. So based on literature review and experience with foaming and bulking at 7 sewage treatment plants in Luxembourg, 5 experimental scenarios were developed and tested at lab scale. We had different aeration modes, different dissolved oxygen concentrations, sludge loadings, feeding regimes, and temperatures. Main factors affecting growth of microtrix and the ability to accumulate lipids were determined. The technology able to select microtrix parvicella was developed, and the lipids accumulated by this organism were characterized. From about more than 20 samples from the lab scale test, we had a yield of 63 milligram FEMS per gram of dry solids, meaning the yield was approximately 6.3% and 98% transesterification efficiency. And this was the best evaluated scenario. The reactor was fed continuously with real wastewater and intermittently aerated. We had a low temperature of 12 degrees and long sludge age at more than 30 days. The samples were taken after 4 weeks of incubation. An increase of microtrix was observed, but as anticipated, we discovered that a longer observation or incubation time would have been necessary for these slow-growing bacteria. Thus, this value is very conservative, and we could expect a higher amount from the pilot. Objectives for the lipid pilot installation are as follows: to operate at real conditions using favorable operational parameters for microtrix, test settlability of the sludge and recirculation, characterize long-chain fatty acids both in influent but also being accumulated in the set of bioreactors, calculate mass balance and evaluate performance of the pilot together with Remondis Aqua, then dispatch the sludge samples to Animox, which will help us to develop the lipid extraction protocol, and then dispatch samples of the extracted lipids to the IRSA Water Research Institute in Italy for the transesterification to biodiesel and assessment of biodiesel quality. Evaluate development of microbial community within the experimental time and in changing seasons at the sewage treatment plant, and to test the feasibility of the technology to eventually give the design recommendation for upscaling. So this is our lipid pilot. Inlet sewage is first being pumped into the mixing tank, which is reducing the large differences in wastewater inlet composition. Thereafter, this water is continuously pumped into a set of bioreactors, which are incubated with activated sludge, as shown here. Automatically controlled anaerobic and aerobic processes are used for the accumulation of lipids and growth of the lipid accumulating bacteria. From the sedimentation unit, part of the lipid-rich sludge is recovered and recirculated back to the bioreactors, while the majority is being stored for later dewatering, extraction, and transesterification to produce biodiesel. Important to note that before the pretreated water is discharged back to be fully treated by the conventional sewage treatment processes, Microtrix presence is being checked, and based on the amount of solids, we add chlorine to make sure we don't cause any operational problems to the sewage treatment operator. Here we have sampling design. So about twice per week, we are writing down flow meter counts and taking samples for suspended solid concentration in the reactor 1 and 2. While once per day, we have a big sampling day with a regular cleaning of the inlet pump and inlet filter. Data are being downloaded from the dissolved oxygen redox potential and pH meters, and samples for the long chain fatty acids, for genomics, for microscopy, for micropollutant analysis are being collected. Here, perhaps to mention also what we expect from the genomics analysis. During the lab scale tests, we found also other lipid accumulating microorganisms. That's beside Microtrix abundance. We are interested to know, of course, what are the other microorganisms which are able to accumulate lipids, and that will be also converted to biodiesel. And here are our first results. Microtrix, as shown on the microscopy picture down on the left, is slowly growing at the optimum conditions. From the first results, as shown down on the right side, the biodiesel yield was also slowly rising up in the last months, currently up to 53 milligrams per gram of dry solids, despite the fact that the inlet water is actually really poor in lipids. We've got about 32 milligrams per liter. That reflects the nature, of the plant we installed our plant at. So we have BOD less than 100 milligrams per liter. We are able to grow Microtrix at relatively prohibitive conditions, and so this is even better confirmation of our technology. So far, we have very good separation of our sludge, as you see in the volumetric cylinders right up on the picture. The three columns, they represent the sedimentation unit in the upper, middle, and low bottom level. So you see we've got really nice sludge being sedimented and thereafter recirculated back to the bioreactors. Obviously, we cannot influence all conditions in the laboratory. For instance, the influent composition is as it is. The same applies for the temperature. We know that Microtrix is growing best in the winter season at microaerophilic conditions, while accumulating best at anoxic conditions. We put these tanks one beside another, actually first time at the pilot, and now we are finding out what will be the outcome. I should note that we learn also to be patient because Microtrix is a slow-growing bacterium. The lipid accumulation is a question of rather weeks to months. And again, I should not forget to mention that we have to be careful not to contaminate the sewage treatment plant with other bacteria. What is good for the lipid accumulation may cause serious problems to the sewage treatment operator. Here is a context of recovery of carbon-based elements from sewage. So our pilot is connected just after screen at the inlet. Beside the lipid pilot, you can also see the other pilots within our VOW project. Cellulose pilot being connected to the fine sieve and the polyhydroxyalkanoids pilot to the primary sludge tank. Within the VOW project, we are currently developing a decision support tool which will help to the sewage treatment plant operators to see which technology would be feasible for their plant and what will be the overall impact of such a technology for their processes. For instance, if I will plug the lipid technology in, what will be happening nutrient-wise in the activated sludge tank and so on. In a short summary at the end, lipid pilot is running at favorable conditions for the selection of Microtrix parvicella and lipid accumulation. Settleability of sludge is still very good. Currently, we have biodiesel yield about 50 milligrams per gram, even in a poor sewage. And we are one step further to circular wastewater. And what are the next steps? It will be the upscale extraction of lipids from the lipid-rich sludge and production of the demo biodiesel and assessment of its quality. All this will be happening within the summertime, as we expect the pilot to be running until the end of August, with the collection and transportation of sludge to Animox. Actually, I sent first samples already yesterday, and we are going to send much more during July, and then at the end when the pilot will be ending. And that's all from my side. Thank you very much for your kind attention. And if you have any questions, I will do my best to answer.
Okay, thank you very much, Zuzana. Are there any questions in the audience? Don't see any hands raised or questions in the chat. Well, I do have a question. Well, you already mentioned in the beginning it has an enormous potential. I think you mentioned something about 4.5 million kilograms, or what was it, of lipids that could be produced? Tons of even more. So that seems very promising. I was wondering, do you have any idea which size is needed at a sewage treatment plant for commercial production, or do you see a combination of several sewage treatment plants in one production facility?
I think it's a super interesting question. To be honest, we didn't do any calculations yet. Yeah, as I mentioned, the sewage treatment plant where our pilot is currently located is actually having very small income of lipids towards our pilot. We still have to do much more calculations to see, of course, what potentially could be the production of biodiesel in a normal sewage treatment plant, and thereafter we can estimate more, I believe.
Okay, so you're not in that phase yet of looking at that, but is that part of the BOW project?
I believe so.
I think so too. Yeah, techno-economic assessment. Yeah. Okay.
Yeah.
Well, considering time, if I don't see any other questions, I thank you again, Zuzana. And of course, you're available to answer questions in the chat if there are any left. I would like to go to our next presentation. We still have 2 presentations left. So our next presentation is again a duo presentation from Veerle Depuydt, who is working at the Flemish Knowledge Centre of Water, Vlakwa, in Belgium, and Tessa Steenbakker of Evides Industrial Water. And Veerle will first give an introduction about the Nereus project with the different demos, and then Tessa will elaborate more on the demo that they developed. So I would like to give the floor to you, Tessa and Veerle.
Okay, thank you. Good morning, everyone. As a project coordinator of the overall Nereus project, I start with a brief presentation, as also Jappe told. This for people who don't know the project yet. Then I will give the floor to Tessa. She will tell us more about their research, about the enzymatic conversion of cellulose into sea source, the recovery of valuable resources related to iron coagulation, and the results of their algae research. Next slide, Tessa. Thank you. Nereus is the acronym for New Energy and Resources from Urban Sanitation, and the main focus of the project is the reuse of water and the recovery of energy and nutrients from municipal wastewater in urban areas. The project started in 2017 and ends this year. Within this project, we set up a demonstration and institutional framework, and this in 4 member states. So we work together with partners in France, UK, Netherlands, and Flanders, Belgium. Next slide, please. Thank you. Next to the demonstration of technologies that focus on water use, energy, and nutrient recovery. We developed also a decision support tool. People who are interested in our decision support tool can join the decision support tool workshop, online workshop next week, the 10th of June. If you want to subscribe, please take a look at our NERUS website. Further, we also focus on community acceptance. And we also have developed different strategies and tools. And one of the tools we also developed is a generic business model. That's a final model. This to give project developers and other people that are involved in this type of projects a first impression of the financial feasibility. You can go to the next slides. Thank you. Of course, we are not doing this from Vito Vlakwa alone. Thus we have a very nice partnership. And the success rate of this kind of project is certainly the willingness to work together and to share information. Within the NERUS project, thus we have 8 partners. On the right side, you can find the people who are involved in demonstrations, who have a demo running within the project. We have Evidis Industry Water, Waterlink, Capso, Deeppurple, and Southern Water. On the left side, we have the knowledge partners, Evidis, the University of Portsmouth and University of Applied Sciences. Thus they collect and handle all the data coming from the demo cases and use them for the development of tools and strategies. Next slide, please. Okay. Here you can see that we have 5 demonstrations. We have 2 in Flanders, we have 1 in the Netherlands, 1 in France, and 1 in the UK. In Flanders, drinking water company Waterlink is testing a pilot train that treats rainwater and grey water till drinking water quality. Another demonstration in Flanders is a demo of Deeppurple at the Nieuwe Dokken in Ghent. It is a new urban district where the Zwienur concept is demonstrated. Zwienur stands for zero wastewater with recovery of nutrients and energy. And the concept focuses on closing loops, water, energy, and the nutrient loop, with as extra dimension symbiosis between the Nieuwe Dokken and the industrial site Krusteens, a soap factory. Partner Capso has a totally different demo. They modified their sludge treatment, this to improve the dryness and heap of the sludge at the wastewater treatment plant at Saint-Omer. And then we also have project partner Southern Water, also a drinking water company. They have tested the possibility to recover calcium phosphate and struvite to reuse as fertilizer. So now we will go more deeply into the case of Evidis Industry Water. This Tessa will tell us more about the demo. So then I come to my final slide. So if you want to know more about all these demo cases, all the tools, strategies, upcoming events that we are planning, please take a look at our NERUS website, www.nerusproject.eu. So thank you also people of the WOW project to give us the opportunity to present our NERUS project and also present the Evidis Industry Water demo case. Thanks.
Okay, thank you, Veerle and Jappe before for the introduction. I hope you can all hear me. So I will show you the results of the demo case in Den Horen, and we are located in the research facility of the wastewater treatment plant of Delft Services BV. So first I will show you the process that we used to get the results, and in general I will tell something about the operation of the process, because we also have challenges there. And then I will focus on the resources we recovered per process step. So this is our process. So the influent is communal wastewater or sewage. And then we first have 2 sieves. The fine sieve screen is actually a belt sieve that screens cellulosic material of toilet paper from the wastewater stream. And we applied enzymatic conversion to produce a sea source. This sieve was located at a different wastewater treatment plant of ours, which was the wastewater treatment plant of Schiphol. And the reason for that is because the Schiphol wastewater contains a high amount of cellulose material. So the process at Den Hoorn actually starts at the drum sieve. The drum sieve is there to simply protect the rest of the stream from large material that comes with the wastewater. Then we have the iron coagulation, which produces an iron sludge. And we tested anaerobic digestion to produce a biogas. And we also did tests on phosphate recovery, so to produce a pre-product. Then we have the nanofiltration, and the nanofiltration is actually the pre-treatment for the reverse osmosis, because we cannot treat the water that comes from the iron coagulation directly into a reverse osmosis. And also the big role of the nanofiltration is that most of the nitrogen goes through the membranes, which results that all the nitrogen, or most of the nitrogen, will end up in the concentrate of the reverse osmosis. And on the concentrate of the reverse osmosis, we created an algae culture with a valuable algae source that also produces a pigment. And we want to extract this pigment in order to create a nitrogen product. And also we use the biomass of the algae culture to anaerobic digest and create a biogas. And at the end of the treatment line, we have the RO permeate, which is actually the clean water created from sewage. In general, so I will focus this presentation on the resource recovery. And on the right, you can see the team that works on this project. So David is our team leader, and Paula is our project leader. And then all the other people are process engineers and also trainees. So we've gained, over the years, we gained quite a few operational experience because treating sewage in this way is quite a challenge. So first we applied, instead of iron coagulation, we applied iron electrocoagulation. And this is a different way of dosing iron into your water stream. You simply apply a current to iron plates in order to dissolve the plates into the water, which then delivers your coagulant. But with the tests we did, we could not reach the requirements of the nanofiltration, so we switched to iron chloride dosing. The nanofiltration, it's quite a challenge to keep the process stable. So this water is very biological active, and this brings challenges. So it takes quite some effort to keep the nanofiltration stable. And with the reverse osmosis, we basically had no challenge. So the previous steps were suited in order to create an RO permeate without too many challenges. So the first step is actually the cellulose to sea source. So the cellulose comes from toilet paper, and the sea source is needed in the wastewater treatment plant for denitrification. And often when the water does not contain enough carbon, this lack is added with methanol or glycerin. And these chemicals have quite an impact on the CO2 footprint of a wastewater treatment plant. And we wanted to see if we could enzymatically convert these fine sieves into a sea source. So here you can see some pictures of the sieves also. So we did this with an enzyme that performed best in acidic environment. And we did several experiments on a lab and pilot scale in order to optimize the conversion. We wanted to see if we could definitely use the product. And we wanted to see what we could do with the leftovers or the waste of the conversion. So this is an example of an experiment with the pilot. So the pilot is basically a reactor in which you add the enzyme with the dry matter, with the cellulose. And what you see here in the graph is that after 1 day, we have a conversion of 66% of the cellulose into a sugary solution, so which would be the sea source. And on the right, you can see how the cellulose transforms from being dry matter into a sugary solution. So after that, we tested the produced sea source with a denitrification test to see if the produced sea source is just as effective as glycerin. So that's normally used as a sea source. And as you can see in the graph, the sea source actually performed a bit better or a bit faster compared to the glycerin. And this indicates that the produced sea source was successful in order to be replace the glycerin. After that, we also did biomethane potential test to see if we could convert the leftovers of the cellulose to sea source to biogas. And as you can see in the text, we were able to successfully convert the leftovers. So the whole process is actually then finished. So we take out the toilet paper with screens from the waste stream, and then we can fully convert it to either a sea source or a biomethane gas. Then the next step is the iron coagulation. So with the iron coagulation, we remove most of the suspended solids, a part of the chemical oxygen demand, quite an amount of the phosphorus, and also a bit of the nitrogen. And most of the iron ends up in the sludge, so only a few percent is left in the watery phase. And after iron dosing, the water is transported into a flocculation tank, or a flocculation tank with a steering that creates the floc formation, and then the sludge is transported to the site, and it can develop a sludge blanket, and then it can be transported to the waste. So we did experiments with anaerobic digestion to produce biogas with the iron sludge, and also this test was successful. Thus, so the iron did not really inhibit the biomethane test, which means that it can be used successfully to produce methane gas. But we saw that this could be optimized by enhancing the pH. So if we increase the pH during the test or before the test, we see that the results are actually better. So in order to optimize the methane productivity, the addition of caustic soda could help to produce as much methane as possible. And then after that, we try to make a design for what the digester would look like then actually, because this is only on a pilot scale. And we came up with a reactor volume of 8.9 cubes. But if we would enhance the pH to a pH of 9, we could reach a reactor volume 5.8. And the amount of gas would be 0.65 cube gas per cube reactor per day. And compared to the digester on the treatment plant of the effluent services, this was quite similar, or even a bit better. Then to the P recovery of the iron sludge. So we measured the amount of 403 gram P sludge, P in the sludge, and this could result into a struvite production of 3.2 kilos per day. But we did measure quite a lot of heavy metals in the sludge, which is a problem with wastewater sludge. So in the table you can see the amounts of heavy metals we measured and the actual amount allowed heavy metals from the government. So this is a challenge. So if you would want to use the P product as a fertilizer, it can not be used in a solid form. So we did some experiments to get the P back into solution, but it did not create the results we wanted yet. Then we go to the algae culture. So the algae culture is on the RO concentrate. And we built, or we let a photo bioreactor be built. And this is a continuous algae culture. And the aim was to grow this algae autotrophically, so without the addition of sugar or a sea source. And so the nitrogen from the RO concentrate will end up in the algae biomass. And this algae, Galderia sulfuraria, produces valuable pigments. And this pigment is called phycocyanine, and it can deliver quite, it has quite a high value on the market. And we selected also this algae because it can cope with harsh conditions. So this algae can grow on in the surrounding with a pH of 1 to 6. So that's very acidic. This can also help to prevent contamination of other algae species. So here is the graph of our photobioreactor. So our researcher Vincent is working on this daily, and just a little month ago we switched the reactor from batch to continuous. And as you can see in the graph, as soon as the reactor is switched to continuous, the growth is limited by the ammonia. So there is some room for improvement in order to enhance the algae growth. So with the current results, we calculated how big of a reactor would be needed to remove all the nitrogen from the stream of the RO concentrate, which is only 50 liters an hour. And we saw that the reactor would need to be quite big in order to remove all the N. So that would be 16 cube of a reactor. And we also saw that the addition of CO2 to the culture is essential for a healthy growth of the algae. And now we are going to test if we can enhance the growth rate by adding sea source after all. Also, mainly because we want the reactor to be a bit smaller. So we hope to aim for a 600 liter reactor. And also we want to see if we can enhance the pigment production. And the reason for that is the next slides. Because we did some experiments to extract the pigment from the algae, and we tried all different kinds of methods in order to get the pigment out, because you need to break the cells in order to get the pigment out. And the conclusion until now is that it's quite hard to extract because the algae is very strong. So we selected an algae that can cope with harsh conditions, but it's also very strong as a result. And we also we want to see if the culture with mixotrophic condition will also enhance the pigment production, because as you can see in the picture, we are able to extract the pigment, but it seems to be very little. So there is still some room for improvement. And in the end, we also tested a BMP test on the algae biomass, and the biogas production was successful, but I don't have the number now. So in conclusion, this is all the goals we had in the beginning, we accomplished. So this demo case clearly shows the possibilities of raw wastewater and what you can do with it and how it can produce very valuable resources. This is my last slide. Thank you for your attention.
Thank you very much, Tessa and Veerle, for a very clear overview of your process and the multiple products that you recover. I see one question in the chat from Joep. Joep, will you ask the question yourself?
Yeah, sure. Thank you for your very interesting presentation. I'm curious what happens with the RO permeate. I mean,
yeah, so in the past, before we were at a different location, somewhere in Rotterdam, and then we were allowed to deliver the RO permeate to a company that could use it for their gardens. So it's actually, it can be used as water for gardens. But this also takes that you need to analyze the RO permeate quite extensively in order to have this permission actually from the government. So at the site of Den Horen, we could not find a partner that wanted to have the RO permeate, but we know it can be used for irrigation water.
Okay, thank you.
Okay. Well, thank you very much. If there's any other questions for Veerle and Tessa, I suggest you ask them in the chat, because considering time, I would like to go to our final presentation. So we can end with a 5-minute delay, I think, of this interesting morning. So I would like to introduce our last speaker. Zuzana already briefly mentioned it. That was a DST developed within the WOW project. And we have Alexander Compeer, who is a researcher at the Center of Expertise Bio-Based Economy at Avans University of Applied Sciences, where he focuses on resource recovery from residual streams. And this morning he will briefly show to you the decision support tool that was developed within the WOW project. So the floor is yours, Alexander.
Thank you, Jappe. If I'm correct, it's almost visible.
Yes, it is.
Yeah, perfect. Okay, well, Jappe already introduced me, and together with Jappe, I'm working within this WOW project, and we developed a decision support tool. So today my presentation will be about this decision support tool. I will first explain you the goal of the decision support tool, what it exactly is meant for, also what you can do with it, the results that you can get from working with the decision support tool. I will also show you some slides of what it looks like. And of course, there's a time for questions. And regarding the time that we have left, I can say I have a relatively short presentation, so we should be fine. First of all, the goal of the decision support tool. So the decision support tool is a tool that was created within the WOW project, which we have already referred to a few times this morning. Basically, due to the legislations, European legislation and national legislations, all on sustainability aspects that we are facing upcoming decades. Basically, this tool was created to support and stimulate organizations, water boards, water authorities to realize their sustainability goals. It's also meant for policymakers. And that could be also, again, within the water authorities or out the water authorities, maybe on a national level, to show the opportunities that there are for recovering and reusing these carbon-based elements that we can find back in our sewage. What is the DST? The DST is basically just an Excel document. So it's an Excel tool that we will provide online once finished. And yeah, as mentioned, it's meant for the water authorities that operate sewage treatment plants. And as you have followed this morning, all sessions, you know, the WOW project is about 3 different carbon-based elements. So we have the cellulose, which can be pyrolyzed, and you get bio-oil, biochar, and acetic acid from it. We also have PHA, which is basically a bioplastic, and that can be produced by microbial accumulation. And also lipids, of which we can make biofuel, biodiesel, and it's also formed by microbial accumulation. Well, what can the DST be used for? It's basically a tool that gives a first impression on a certain influent stream of a sewage treatment plant to say whether it's suitable or not to recover one of these carbon-based elements. Well, how is that done? I will show a few examples as mentioned in later slides, but we use a certain limited amount of parameters that you should fill in, and then the outcome of the DST can be used to decide whether or not it's interesting to have a closer look if you can implement these techniques, yes or no. So then the results. If you have filled in the results, or if you have filled in the parameters within the decision support tool, the decision support tool will show you the outcomes, the results, and that's an indication. The first result could be that either the implementation of one of these techniques is promising. It can also be that we think based on the tool and the parameters that are filled in, that the techniques to either recover cellulose, make PHA or lipids, it's not feasible. Or a third option in which we think it's not yet clear if the implementation is possible, and more detailed consideration would be required. So next to the results of the possibilities of implementing the recovery of one of these 3 carbon-based elements, we will also provide information within the DST about this recovering techniques. First of all is that we also show the side effects of implementing one of these techniques. You can see the side effects on the regular processes within the sewage treatment plants in the kind of a fact sheet, which is also included in this decision support tool, which I will also show on the next slides. Next to those side effects, we also have kind of a fact sheet about the technical aspects, which are based on the information from the pilots, which we have seen in the presentations this morning. Also, the economic aspects are mentioned, the main economic aspects, and those are based on the techno-economic assessment, which is being performed within this project. And we also have some environmental and sustainability aspects, which we will mention, also information from coming from the pilots. And last but not least, we also have included some social aspects. Then I'll walk you through the decision support tool in short. The decision support tool was an Excel document, as I mentioned. Basically, this is the first tab you can find, which is explaining the decision support tool, well, what it is, but also how the decision support tool works. And that can all be found on the first tab if you open the decision support tool. So this is a print screen of how that will look like, and if you scroll down, there's also an instruction on how to use this. Then if we go to the second tab on this tool, it looks like this. So this is called the input tab. So this is the tab where you fill in basically some parameters of your sewage treatment plant, or even better, or even more easy. You can fill in multiple sewage treatment plants at the same time, as you can see in the table. At this moment, you can fill up to 50 sewage treatment plants, in which you can fill in different parameters, or you should even fill in. It's not good, it's should, because else you will not get any results. So basically the name and the location, it's wise to do that so you can identify the sewage treatment plants for which you're filling in your parameters. The first real parameter is if there is a primary treatment at the sewage treatment plant, yes or no. Then there's a parameter indicating the percentage of sewage which is coming from households. And there are 3 options you can choose from a drop-down menu. You can either choose if it's less than 25%, between 25 and 50%, or over 50% coming from household waste. Then the next parameter is about the population equivalent of the sewage treatment plant. So it says something about the size, the capacity of the sewage treatment plant. And the last parameter you should fill in is either BOD or the COD. It can be chosen one of the two, because we also need a BOD-COD ratio. And in order to calculate that, we need either one of the two parameters. If you have both of them available, it's even better if you fill them in both. If not, we have also set a standard value for the BOD-COD ratio. You can see it in the red cell. We've put it at 0.5 at this moment, but it's adaptable. And if you go to the next step within the tool, you go to the overall results. As I've already told, the overall results can be shown in 3 ways. Here we see a table in which we have filled in 10 fictive sewage treatment plants. And you see for each of the 3 recovery techniques, the PHA, the biodiesel, and the cellulose, if they are either suitable, promising for this technique, yes or no. Not feasible, then they're colored yellow. And if you need to look in closer detail, then it's colored gray. So next to the table, you also have some pie charts in which is shown in a different way the amount of promising sewage treatment plants for a certain recovery technique. And we also specified that into tabs for each technique. In this case, we have shown the tab for the PHA recovery, where we indicate even per parameter if it's the lacking or not the lacking parameter. So basically you see here for primary treatment, all the 10 examples have primary treatment. So that's a positive thing. It's a requirement in this case for recovering PHA. That's colored all green, but you can see in the amount of population equivalents, for example, only 3 of them are colored green. The other ones are colored yellow, or there's still one gray one, but that yellow indicates that it's probably too low amount of population equivalents. So the capacity of the sewage treatment plant is too low to recover PHA. It's not possible, or not yet possible at least. Of course, you can think of other solutions. You could combine different STPs together, maybe if they are close to each other, and you could decentralize the processing of recovering PHA as a possibility. But at least for this sewage treatment plant only, it's probably not possible. That's the indication that it gives. We also have included the fact sheet, as I mentioned. Here are the fact sheet, and this one is the one for recovering cellulose, where you can make where you can perform the pyrolysis on. But recovering the cellulose, basically this tab is showing what effects that will have on the other processes within a sewage treatment plant, or the general processes within an average sewage treatment plant. And again, it says something about if it has no impact on this process, or if it has a possible impact on the process, or it will definitely have an effect on the process. And well, it's indicated with colors, as you can see, and also within the red triangle in the corner of the cell. If you go with your cursor on that, it will give an explanation about why or what. And as last, we have, as mentioned, also some specific additional information on the techniques regarding technical aspects. So you can think about, yeah, well, you can see in here dimensions or the status of the technique, the use of electricity or chemicals, which are included. We also have some economic aspects on which we try to say something about the CAPEX and the OPEX, aspects like that, prices of the products that you get from recovering these techniques. And next to that, also the environmental sustainability aspects of this technique, or in this case also including the pyrolysis of the cellulose. Aspects you could think of like odor or noise, visual aspects are all described in this fact sheet. And also social aspects like health and safety or legal aspects that are relevant. So that's something we are still busy with. We are still developing this and trying to complete these fact sheets and optimizing the DST. The DST is already being tested. We are now in a second phase to optimize this tool. And well, once finished, we will publish the tool online, and it's available for use. And that will be roughly after summer. That's my presentation about the DST.
Okay, thank you very much, Alexander. Are there any questions for Alexander about the decision support tool? Well, I don't see any hands raised. Yeah, I see one, I think. I have to take a look who's raising his or her hand. Otherwise, I would give you the floor. So if you have a question, feel free. No, it's disappeared again. So then, well, thank you very much, Alexander. I'm not going to ask you a question because, well, I'm part responsible for the DST, so that would be a bit weird. So thanks again for presenting the DST. So this also completes our last speaker for this morning, and I would like to once again thank all the speakers. I think they gave a nice overview of all the new developments that are taking place in resource recovery from residual streams. So thanks again. We'll ask all the speakers if the presentations can be made available, and if they agree to this, then we will share the presentations with you as a PDF. And of course, if you have any questions, don't hesitate to contact the speakers. I think they like that if they get questions about what they are working on. At least I always do. Well, to finalize for today, I would like to tell you that with WOW we organize several other activities during the EU Green Week. So even this afternoon we have a policy debate because it wasn't mentioned a lot, but there's always legal restrictions with the reuse of resources from sewage or other residual streams. So if you're interested in that, you can still join the policy debate. And also we have 3 online pilot visits for all the pilots that were presented this morning for WOW, and also Veerle already introduced activities from Nereus. So look at their website and look at our website. I will post it in the chats in a minute, the link to our website, and there you can link to the online events. And then I would like to thank everyone for joining this morning, and I hope you all have a good day, and hope to see you some time later, hopefully incorporating in one of the projects, because I think there are very interesting links to work together. So thanks again and enjoy your day. Bye everyone.